So the name of the course was Beyond the Event Horizon. All right, so it was an investigation about time travel in parallel universes. I picked this title, and you'll know why shortly within an hour. It's a very apt title. So everything's about time travel. Is time travel possible? All right. All right. A lot of you guys are skeptics, or at least you like to. A lot of you guys like to say that you guys are skeptics, and despite the fact that deep down, most of you guys believe in time travel, and most of you guys like to believe in time travel. You may be in denial, but I know that about 99% of you guys are believers in time travel. This is almost like preaching to the choir. You're not usually, you guys are not the right people for this lecture, because I'm not going to try to convince you that it's possible. I'm not going to try to convince you that it's not. We will do a scientific investigation, but I'm always curious as to who the skeptics are initially. All right, so my starting point is always a simple thought experiment. All right, it's what I'm about to say is 100% science fictional. All right, and this is the sort of stuff that you would see in science fiction movies. What if time travel were possible? What if we had the technology? If we had the technology, I could literally travel 100 years into the future, spend 18 hours there, and come back with the next fraction of a second. All right, without you guys even noticing, I made 3 statements. Within a movie setting, you're not going to find anything wrong with it. I have a time machine. I'm traveling 100 years into the future. I'm spending 18 hours there. I'm coming back with the next fraction of a second. All right, you can write a script on it. You can make it work. Except if you're looking at it from a reality perspective, all of a sudden you go, wait a minute, there's an assumption here. One of the statements contains an assumption which may or may not be correct. If you're a skeptic, you would zero in on that assumption immediately. There's an assumption that makes time travel possible. So the question is, what is the assumption which may or may not be correct? All right, so let me just make 3 statements. Now I'm going to let you guys think for like 10 minutes, 10 seconds. You guys don't get 10 minutes. All right. If time travel were possible, assuming that we had the technology for it. All right, so I'm going to travel 100 years into the future. That's statement number 1. I'm going to spend 18 hours there. That's statement number 2. And I'll be back with the next fraction of a second. That's statement number 3. All right, so one of these statements may or may not be correct, but it's crucial for time travel. So which one becomes the question. So you don't need to say anything. Just think about it and check to see which statement, as far as you're concerned, is absurd, nonsensical. Could never happen in real life. In movies, maybe, but not in real life. So traveling 100 years into the future, spending 18 hours there, and coming back with the next fraction of a second. All right, now that you guys thought about it briefly. All right, guys, let me just clarify a few things. If you're thinking traveling 100 years into the future, I got news for you. If you got a time machine, you should be able to travel 100 years into the future. That's fine. Spending 18 hours in the future, I spend 18 hours any day. I actually spend more than that, more than 18 hours a day, every single day, ever since I was born. I have no problem spending 18 hours a day in the future, in the present. Never had that problem in the past either. So that's not a problem. A lot of you guys will say, wait a minute. You spend 18 hours somewhere else and you'll come back with the next fraction of a second. That cannot be true. If you're thinking that's the problem, absurdity in what I just said, I got news for you. Deep down, you believe in time travel. All right, because most of the people usually focus on that. Wait a minute, you spend 18 hours somewhere else and you'll come back with the next fraction of a second. I don't think so. In fact, if time travel were possible, I could spend 18 hours somewhere else and be back before I leave. I'm just being kind to you that I'm arriving a fraction of a second after I leave, in essence. All right, I get to decide when I'm going to come back. That's time travel, guys. There's no problem with anything that I said, except for the first statement. I said, there's no problem. If I have a time machine, I can travel 100 years into the future, provided that 100 years in the future is already happening. Just like the present is happening, just like now is happening, guys. Is it? Do you think that the future is already happening? Do you think that the future is just as real? Same question. Do you think that the past is already happening? Do you think that the past is just as real as the present is? Can you go to a place that doesn't exist? Can you go to a time that doesn't exist yet? And so that question is no. All right, future will potentially happen. Hasn't happened yet. Can you go to a time period that has not yet happened? Nope. Can you go to the past, which happened in the past, obviously? Do you think that the Hitler is still conquering Poland? Can you go back to World War II? The answer to that question is no. Past happened, it's not happening. The future hasn't happened, potentially can happen. The only thing real is the present. So all of a sudden the question is time travel possible? The answer to that question is yes, but we were doing it 1 second at a time. So can you leap 100 years into the future, spend 18 hours there, and come back with the next fraction of a second? The answer is absolutely not. Can you go back to the past? Not a chance. What you see is what you get, guys. Nothing exists outside of the present. So if that's the case, is time travel possible? No, 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 hell no. It's absurd, it's nonsense, and these are the arguments that you will get from skeptics. All right, that's your common sense. That's your common sense talk. And you guys know what I think of common sense. It's just garbage. I'm very surprised that it did not get evolved out of our lives as yet. All right. Nature has nothing whatsoever to do with your common sense or my common sense. Einstein will say, future is just as real as the present, and the past is just as real as the present. As far as Einstein is concerned, the future, the past, the present, all happen and coexist at the same time. How do we know that? Because that's the basis of Einstein's theory of gravity. Time is a continuum, which means that the past, the future, the present, all equally real and all happen at the same time. Our experience of time is from past to the present and from present to the future. I got news for you guys. Everything that you're experiencing is already part of the space, the fabric of the space-time continuum. It's almost like a four-dimensional movie in Einstein's reality. So does this mean that the backward in time travel could also be possible? Forget about the future. How about going back to the past? And then the question of the parallel universes, do they exist? Why do we even need the concept of parallel? We'll find out. This is going to get real interesting. It's going to get real weird. I got news for you. Gravity in Einstein's theory is not a force. Gravity is what you experience when masses warp the space-time continuum. Gravity is the curvature of the space-time continuum. That's it. Space is a continuum, so is time. We would not have gravity if we did not have the future, and we would not have gravity if we did not have the past. No future, no gravity, no past, no gravity. Time is a continuum. The future, the past, the present, all exist at the same time. And they form, combined with space, it forms a space-time continuum. And then you warp the space-time continuum, and that turns into gravity. All right, so that's the continuum. So there are three conditions that need to be satisfied in order for time travel to be possible. Condition number one, time has to be a continuum. So according to Einstein's theory of gravity, it is a continuum. All right. The second condition for time travel is space-time continuum needs to be curved. If it's flat, you don't have a chance. It needs to be curved, and there's a reason why it needs to be curved, as you will find out.
This is a Mobius strip. One surface, one side. Here, try it. Make a line on it.
This is wonderful. This is a Mobius strip?
Yeah.
I'm going to show them that at school.
All right, so this is a scene from the movie Infinity, based on the life of Richard Feynman. Happens to be the best physicist after Einstein. All right, so we'll talk about him towards the end of the semester. All right, in every single movie, if it's a time travel movie, and they show you something, they usually give you the Mobius strip. Instead of the space-time continuum being flat, you end up getting a curved space-time continuum. All right, so it's a possible shape of the space-time continuum that you will get to see in a lot of the science fiction movies. So why do they just warp the space-time continuum? Why is that they curve the space-time continuum in these time travel movies?
People there.
Here's the reason why. You're looking at it. This guy.
And I was standing off in a corner, sort of watching quietly for a few minutes, relaxing. And Stephen was over there not far from me. Jane walked over to Stephen and looked at him, and he was sitting there with his head in his lap, like only Stephen can put his head in his lap. And Jane said to Stephen, "You look miserable, Stephen. Sit up straight. Some of your guests don't understand that you're sitting there thinking about physics and having a wonderful time. It looks like you're in pain. Sit up straight and go talk to your guests."
All right, this guy's name is Skipthorne.
There must have been 50 people.
More than likely, this is the first time you're seeing him, despite the fact that this guy is one of the biggest names in physics. He won the Nobel Prize about 3 years ago for the LIGO project. One of the biggest theoretical physicists, and this guy made time travel possible for us. He's talking about Stephen Hawking, his best friend. All right, so he's recently retired. I think he retired a couple of years ago from Caltech. He was a full-time professor there.
Sagan, the noted astronomer, was writing a science fiction script called Contact, meeting
And here's the backstory.
extraterrestrial life forms. But he had a problem. The distance between stars is so great that it would take centuries to visit other planetary systems. And because of the time dilation problem, he decided to ask a physicist, is it possible to go these enormous distances in a twinkling of an eye?
Sagan called Professor Skipthorne, a noted expert on Einstein's theory. Thorne struggled with the problem for some time. Then, in the back of a Ford Bronco, as he was driven along Interstate 5, he made one of the most inspiring connections of modern physics by linking Carl Sagan's cosmic conundrum with the exciting new concept of wormholes.
A wormhole is a hole in space that may give us a shortcut between 2 points. For example, if I had a super microscope and I could peer right into the fabric of space and time, I would find that it's not smooth at all. It's foamy, it's frothing, with tiny little holes and bubbles. If science can somehow tease apart one of these holes in space, we can actually connect two distant regions of space and time. Now, where have you seen that before? In Alice in Wonderland's Through the Looking Glass. The wormhole was Alice's looking glass that connected the countryside of Oxford with Wonderland, such that when Alice stuck her hand through the looking glass, her hand went through the wormhole and came out on the other side of forever.
Thorne was triumphant. Wormholes were an exhilarating means of connecting 2 points in space. It was only later that the full implications hit him. If wormholes could cheat space, they could also cheat time.
Sagan.
All right, so Carl Sagan, the famous astronomer, or used to be before your generation. Those of you guys who don't know, this guy's like one of the biggest names in popular culture. Was writing a novel, Contact. That later became the movie. I think I'm going to make this an assignment for you guys, so you will get to watch it. And I will have a bunch of questions regarding that. And so the question is, she had a main character, and the main character was supposed to be able to travel to the Vega star system, which is located like 26 light years away. For the movie to make sense, she was supposed to be able to get there within a fraction of a second and spend 18 hours there, and then be back within the next fraction of a second. Okay, it's kind of like my observation that I gave you, the thought experiment in the beginning of the lecture. Remember I said, if we had the time machine, what if I could leave 100 years into the future, spend 18 hours there, and come back in the next fraction of a second? It's exactly the same thing. All right, so I kind of stole the idea from Contact in essence. So Carl Sagan's question is this possible? All right, so Carl Sagan is a big name and Kip Thorne is a big name. They're good friends. So he calls up Kip Thorne and says, what do you think? I mean, is it possible? Is something like this possible? So Kip Thorne was thinking about it. Initially, he thought, no, this is nonsense. It's just complete science fiction. So he's in the back of a Ford Bronco, Interstate 5 in California. And then the idea just occurs to him that, yeah, why not? If space-time continuum is curved, you can, in theory, you should be able to take shortcuts through the space-time continuum. And these shortcuts are known as wormholes. I imagine that the space-time continuum looks like the Mobius strip, so we're just borrowing an idea from science fiction. So space-time continuum, spaces, X, Y, Z dimensions. So this is what you're experiencing at this moment. So you got your time as well as space dimensions right here. This is the present. This is a point in the future. This is a point in the past. Everything is happening at the same time. Despite the fact that your consciousness is here, your awareness is here, the future is already happening, so is the past. So instead of just traveling through the space-time continuum 1 second at a time, why not just take a shortcut? So the question is how? Because these hypothetical shortcuts, the wormholes. So the question is there such a thing?
Going forward in
Are there real wormholes?
time at near the speed of
Natural.
light is relatively easy. Traveling backward in time seems all but impossible now, but it isn't ruled out by Einstein's theory. If Joe Tanner in his super shuttle wanted to go back in time, he would have to locate a black hole. And not just any black hole, a special black hole connected to another light years away. The resulting tunnel in time and space is called a wormhole.
All right, so the first thought is, can we take shortcuts through the space-time continuum? The answer to that question is, well, it depends. If space-time continuum is flat, forget it. But if it's curved, yeah, in theory, you should be able to take shortcuts. How so? Well, do we have black holes today? Of course we do. Did we have black holes yesterday? Most definitely we did, right? And how certain are we that we're going to have black holes tomorrow? Again, the answer is yes. What if these black holes somehow become connected? If they become connected, they become shortcuts through the space-time continuum. So those are known as wormholes in theory. So two connected black holes will make a wormhole. So the next question is, wait a minute, can you really travel through two connected black holes? The answer to that question is most definitely not. Okay, that would be insane, because how do you know if it's a black hole or a wormhole if you're looking at it from outside? There's no telling. All right, you can't tell what's going on inside a black hole. And number two, even if you were to jump into it, assume that that's a wormhole. All right, if you have advanced knowledge because you had a dream about it, and then you jump into one. Gravitational tidal forces would shred you to pieces. Radiation would vaporize. All right, it would destroy you. Jumping into a black hole is one of the worst things you could do in essence. And time travel, even if it's a wormhole, would be impossible unless somehow you can stabilize that black hole into a wormhole. So you can just get rid of the tidal forces, you can control the radiation, and everything would be fine. So the question is, how do you stabilize a wormhole so you can do time travel for it? Well, what you need is something that can cause repulsive gravity. So you need to have a certain special sort of matter that's going to generate enough repulsive gravity to keep the black hole stable and open long enough for you to be able to travel through it. So the question is there such a thing in the universe? Now, Skipthorne was coming up with these ideas in the 1980s. All right, there was no such thing in the universe that would generate repulsive gravity back then, as far as physicists were concerned. So he called this matter that was supposed to be generating repulsive gravity, he called it the exotic matter. Is that if you had some exotic matter that could generate repulsive gravity, you can stabilize a wormhole, you could keep it open long enough in order to do time travel. Basically, that was the whole idea. And then something happened in the 1990s. Physicists discovered that the universe was expanding. No surprise, we knew that all along. That wasn't the surprising thing. What was surprising was, as the universe was expanding, we discovered that the universe was accelerating, which means that it was speeding up. And then accelerated expansion, because initially we thought the Big Bang started, the universe started to expand. We thought the expansion was slowing down. And if we were lucky, it would stop expanding at some point, it would stabilize itself. If we were unlucky, the universe would start to collapse back to its initial point. Right, that was called Big Crunch. Okay, so there was no thought that this was going to keep. We didn't think that this thing was going to accelerate or speed up. We never expected the expansion to speed up. Now, for it to speed up, which means that there's something within the universe is generating repulsive gravity. Something is pushing the universe in the outward direction. There's nothing else on the universe that's going to pull the universe in the upward direction because it's a universe. That's a single universe, obviously. So whatever is pushing the boundary in the upward direction is coming from within. And all of a sudden, the physicists said, wait a minute, something in the universe is generating tremendous amount of repulsive gravity, enough to cause an accelerated expansion of the universe. What that something is, completely unknown. Hence the reason it's called dark energy. It's the same as Skipthorne's exotic matter. We don't know what it is, but the universe contains tremendous amount of dark energy, which is responsible for the accelerated expansion of the universe. So the question is it possible, if one day we figure out what this dark energy is it possible to stabilize some of these black holes into wormholes so that we can do time travel? Can we create time machines, if that's the case? So we shall investigate. So the author of Concept is Carl Sagan. All right, so the idea of time travel through wormholes is from Skipthorne. So B. All right, so 3 conditions need to be satisfied. Number 1, time needs to be a continuum. Number 2, space-time continuum needs to be curved, so we can take shortcuts. And there's going to be a 3rd condition that needs to be satisfied.
Suppose a wormhole does twist time as well as space. Suppose NASA engineers were able to keep 2 wormholes open and connected using a repulsive gravity source. Suppose the super shuttle could navigate through the connecting tunnel. Suppose they found Elvis out there. Suppose. Cosmologists do a lot of supposing.
Now, one of the theorems that was proven many years ago is that if you create a wormhole in a region of space where it never existed before, you must also twist time in such a way that time travel becomes possible. In other words, not only do you have created a hole in space, you must also have twisted time around so that it becomes possible to return to your starting point in space-time before you left. You automatically create a time machine when you create a wormhole.
All right, so through wormholes, you should be able to travel, take shortcuts through the space-time continuum, which means that you should be able to travel to the future, 100 years from now, spend 18 hours there, and be back in the next fraction of a second. Likewise, if you can go to the future, you should also be able to go back to the past exactly the same way. Just take a shortcut to the past. Except immediately you will notice a problem. The problem is this: what if I could travel back into the past, right? Just if I had to take a vacation, going to the past is kind of interesting because We already have a map of the past, which is known as history. It would be fun to see how much of the history you can change by going back to the past. What if I could just go back to the past and find Hitler and kill him before he starts World War II? Then what happens to World War II? What happens to the history if you could just find him and kill him? All right, now there are a couple of problems with that one. Number one, by the time Hitler looked like the way we imagine him to be, guys, you could not go near him. It would be out of the question. It was well protected. All right, so which means that you have to go back, preferably find him as a kid, and look for a kid with a funny mustache, basically. All right. Does anyone know what he looked like in essence when I was a kid? I mean, that's not what the kids look alike. Are you just gonna kill every single kid named Adolf? Is that the way it's gonna work out? And what would happen if you could just kill him? What happens to World War II? All right, let's make it a little bit more personal for you guys. All right, forget history. Let's talk about you, everybody's favorite topic. Why don't you go back to your own past, find your grandfather before he fathers your father, and kill him? What happens to you then? You know what's gonna happen. You're gonna vanish. You go back to the past, find your grandfather before he fathers your father. You will vanish. Boom. You kill him. As soon as you kill him, you're gone. If that's the case, who goes back in time and kills your grandfather? No one. He's still alive. You're still born. Go back in time, kill him again. You vanish. Because you vanish, no one goes back in time and kills him. He's still alive. It's called a paradox, guys. It's otherwise known as a grandfather paradox. Time travel back to the past will cause time travel paradoxes. So how do you overcome
Is what's called the grandfather paradox.
Told you. So how do you overcome the grandfather paradox? If you can travel into the future, by the same means, you should be able to travel back into the past. If physics does not prohibit time travel into the future, physics cannot prohibit time travel into the past either. All right? If that's the case, what could stop you from killing your grandfather before he fathers your father? Nothing. Except nature does not like paradoxes. All right, so which means that for time travel to be even possible,
The grandfather
active time travel needs to create its own parallel history, which means that you should be able to go back in time and be able to kill your grandfather without vanishing. If you're killing your grandfather, you're killing your grandfather in a parallel history, in essence. You cannot change the history of this universe. You're simply creating a new branching universe, a branching history.
paradox says, if time travel is possible, then it ought to be possible to go backwards into time and kill your grandfather before he fathered your father. Then you've got problems.
You might tend to vanish if you shot your own grandpa, but Tytler says that quantum mechanics provides a theoretical solution. Quantum theory holds that each atom goes through all possible histories. Tytler asks us to think about such a universe, or multiverse. He supposes you would have killed a copy of your grandfather in another branching universe.
In that history, which you're now in, he does not father your father. You do not exist in that history. As a young man, anyway, what you have done is you have entered that history via the time machine. Now, if we could isolate ourselves, we would also be aware that we existed in any of the universes. It's the very fact that we're, so to speak, anchored to one of these universes, because we are interacting all the time with the other atoms in this universe, that we're unaware of the other universes.
All right, so the third condition that needs to be satisfied is the act of time travel. It needs to create its own parallel history. All right, all these three conditions need to be satisfied for time travel to be even plausible. All right, so that this course becomes an investigation whether or not we can satisfy all three conditions, which means that all three conditions will require enough evidence for us to go, okay, so it may be possible. Okay, guys, you may end up getting a different answer depending upon your life circumstance, but the only way you can overcome the grandfather paradox, the act of time travel needs to create its own parallel history or universe, right? So B is the best answer for that one. Well, is this just science fiction or is this real science? I got news for you. The parallel histories, otherwise known as the mini-worlds interpretation, was this guy's PhD dissertation. His name is G. Everett, which was published in 1957. At the time of the publication of this theory, I think there was only one person here on Earth who believed in this theory. That was him. Today, this is the mainstream interpretation of quantum theory. At first glance, it kind of irks you because it sounds so science fictional. And then when you think about it, his explanation is going to make a lot more sense than the orthodoxy that we've been using, which is known as the Copenhagen interpretation. All right, so the quantum theory, it's got two main interpretations. One of them is called the Minimalist interpretation. So this guy is responsible for it. We have it. The second one is the Copenhagen interpretation, which is the orthodoxy of quantum interpretation, which is known as the Copenhagen interpretation. Regardless of which interpretation you're looking at, quantum theory works. Just about the best theory ever invented by human beings. Without the quantum theory, this Zoom meeting would not be possible. Your cell phones would not work the way they do. A lot of the technology is based upon quantum theory, modern physics. All right. So the question is there any evidence for these parallel universes or parallel histories, so to speak? Is there any evidence, supporting evidence for the minimalist interpretation? So that's one of the things that we will get to next year.
I've heard that there's a possibility that in string theory that there are multiple universes being created at any single moment.
It's an idea that comes into the theory, also comes into theories of cosmology.
So there could be multiple us at this moment.
There's a theory that says something akin to that we're having an interview, and the other
number
universe,
of us.
the interview is different in the other universes.
In some of the universe. Could I have nailed you just now?
I just heard that you did from the other one.
Oh, really?
Yeah.
Maybe I nailed you in this universe.
You did indeed.
Would you please come back?
Sure, happy to.
Maybe I'll understand it next time. Brian Greene, we'll be right back.
All right, guys, you will get to know Brian Greene quite well. We're going to be watching some of his documentaries. So here's the big picture of what we will be doing.
On Nova, take a thrill ride into a world stranger than science fiction, where you play the game by breaking some rules, where a new view of the universe pushes you beyond the limits of your wildest imagination. This is the world of string theory, a way of describing every force and all matter, from an atom to Earth to the end of the galaxies, from the birth of time to its final tick, in a single theory. A theory of everything. Our guide to this brave new world is Brian Greene, the best-selling author and physicist.
No matter how many times I come here, I never seem to get used to it.
Can he help us solve the greatest puzzle of modern physics? That our understanding of the universe is based on two sets of laws that don't agree. Resolving that contradiction eluded even Einstein, who made it his final quest. After decades, we may finally be on the verge of a breakthrough. The solution is strings. Tiny bits of energy vibrating like the strings on a cello. A cosmic symphony at the heart of all reality. But it comes at a price. Parallel universes and 11 dimensions, most of which you've never seen.
We really may live in a universe with more dimensions than meet the eye.
People who've said that there are extra dimensions of space have been labeled crackpots, or people who are bananas.
A mirage of science and mathematics? Or the ultimate theory of everything?
If string theory fails to provide a testable prediction, then nobody should believe it. Is that a theory of physics or philosophy?
One thing that is certain is that string theory is already showing us that the universe may be a lot stranger than any of us ever imagined.
All right, so three conditions need to be satisfied. Time needs to be a continuum. And according to Einstein's theory of gravity, it is, which means that the future, the past, the present, all need to happen at the same time. So the question is Einstein's theory of gravity proven to be correct? Or is this just a theory or a scientific fact? So that requires an investigation. How about the shape of the space-time continuum? Is it flat? If it is, no time travel. Is it curved? Then we can talk about time travel, because we may be able to take shortcuts through the space-time continuum by creating time machines, artificial wormholes. And lastly, for time travel to be possible, the act of time travel needs to create its own parallel universe, which means that the many worlds interpretation has to be correct. There has to be evidence for the many worlds interpretation. All right, we need to have parallel histories in order to overcome time travel paradoxes, which usually happen every time you travel back into the past. All three conditions need to be satisfied. So when I was building the course, because this is science, so I decided to do seminars class in time travel. So we would just keep up with the research regarding whether or not time travel was possible. So we decided to focus on these three questions. Is there any evidence that the number one is Einstein's theory of gravity? Is it proven to be correct? Is that a scientific fact, or is it something that we could use to come up with time travel science fiction? Space-time continuum, flat or curved? It needs to be curved so we can take a shortcut. And furthermore, if this is the only universe, I got news for you guys. If Einstein is correct, if this is the only universe, forget time travel. It cannot be done. All right. If you cannot time travel back to the past, you cannot time travel into the future either. Okay, because physics does not distinguish future from the past and past from the future. Time does not have a direction in physics. And if going back to the past is going to cause time travel paradoxes, and nature is not going to allow that. The only way you can overcome time travel paradoxes is the many worlds interpretation has to be reality, which means that the active time travel should create its own parallel history. What that means is the parallel histories must be created at all times. So the question becomes, is there any evidence? All right, so the interpretation is not science. You got the main world's interpretation, it's philosophy. Is there any evidence regarding the possible existence of these parallel histories, the parallel universes? And when I was coming up with these three conditions that needed to be satisfied, I was thinking, okay, so we can figure this out. This is straightforward. Space-time continuum is a flat or curved. I mean, this is not a big deal. Einstein's theory proven or unproven. All right, these are like, you can come up with these answers within less than a minute. And then I figured that, hey, we were just gonna get stuck here. All right, we were gonna make the argument of time travel without being able to prove it, and science requires evidence. I figured that there's no way there are parallel universes. There's absolutely no way. I mean, I love science fiction, but I live in reality. My thought was not a chance, because I thought time travel was nonsense. I didn't think it was possible in the way it is done in science fiction movies. And then something happened along the way, guys. Some quantum weirdnesses started to take place. They start building these quantum computers, and the quantum computers are based upon the main world's interpretation. And all of a sudden I go, oh, this is so weird, as you will discover, and you will, that this time travel may be plausible. All right, so that's the conclusion that we're going to start to move towards. All right, so this is the big picture of what we will do.